Hello everyone, welcome to Dakshana e-classroom program. So in last lecture we talked about few terms, that is chalk coil and some circuits and calculating like voltage current. So and we saw some application of them, so I hope you are clear with that. And before that we talked about phasor diagram and calculating like I, current, voltage, finding phase, power and all those things. So I hope you enjoyed that. And the next topic we are going to talk about is series RLC circuit. So the means like we R stand for resistance, in the L for inductance and C for capacitance. When all these three elements connected in a circuit in series, we call this is series RLC circuit. So exactly in same manner, just like we did for RC, RL, LC circuit, calculating different things, impedance, reactance and all that. Let's first do the calculation, and this circuit is a little bit special. Something special about it is there. I will tell you what is exactly special about it. So let me first so this is our circuit. Let's say resistance, inductance, capacitance connected all in series, and this is our voltage source and some current I will be flowing in it. So first thing is we must remember to solve this. We must remember the phase relation between current and voltage across each of these elements. I hope you are already remembering that. So let me first draw its phasor diagram because it helps us a lot. So for drawing phasor diagram, because all three elements are in series, so which quantities should be taken along x-axis, and that is current. Correct. So let me write, let's say this is I is the current in the circuit. Then I can write whatever the potential drop across resistor. So VR will be in same phase as I. So this is VR. If I is the current in this circuit, then what about potential drop across inductor? So potential drop across inductor leads the current by 90 degrees. So I can add VL will be here, and potential drop across capacitor lags this current by 90 degree. So VC should come here. So this is your phasor diagram. So now depending on either VL may be greater than VC, that will depend whether XC or XL, whichever is larger. So in this situation, if I take that VL is greater than VC, then overall this is VL minus VC will come here. This is VL minus VC, let's say. Then my net voltage will be here. This is your V. Clear? And this is our phase angle phi. Right? I hope everything makes sense to everyone. So we got net voltage and this will be along the phase. So in this situation you can get it actually like here. If this condition is there, then effectively this circuit is acting like an RL, R and L circuit. So here in this situation your current is lagging behind voltage by a phase angle of phi, and voltage is leading current by a phase angle of phi. Okay, so this is all. So I can write here now, because these are exactly in opposite phase, is it there is possibility that this exactly become equal to this? In that case what will happen? There will be no potential drop across this. Can you imagine it? So VR, VL and VC. That means if polarity here is this, then polarity here is that. This is the meaning of this positive negative phase. Are you getting it? I is the current flowing in this circuit. So if the potential drop across this is in this polarity VL, then potential drop across VC will be of opposite polarity. So it's minus and plus. Right? Okay, so I can now in this case I can write my net voltage. So the net voltage drop, I can relate it, V is equal to what? Under root VR square plus VL minus VC whole square. Is it? And what is VR, VL, VC? So that I can write, if current in the circuit is I, then I can write VR is equal to I times R, VL VC will be equal to I into XC. So I hope you are already clear with what is that term XC, and VL is equal to I into XL. But still I will tell you what is L. So if I substitute everything there, then what I am getting, and let's say Z is the impedance of circuit, net impedance of the complete RLC series circuit. In this situation I can write V is equal to I times Z, and this is equal to what? Under root I R square I XL I XC whole square. Clear? And if I cancel everything from like then I'm getting this is under root R square plus XL minus XC whole square. So this is the impedance of circuit, correct? And I can be also written as I is equal to V divided by Z, and that is under root R square plus XL minus XC whole square. Remember here, even if you are writing here XC minus XL whole square, there is nothing wrong. That is exactly same, because you can just imagine mathematically XL minus XC whole square, it doesn't make sense whether it's XL minus XC or XC minus XL. So it's same thing actually. So we got the impedance, we got the current, we can calculate the phase angle, is it? So I am writing here in general term, and that too by considering this situation. If the situation changes, I don't think you should have any problem in changing the things according to that condition, right? So here I can calculate the phase angle, the phase difference between V and I, so that I can calculate tan phi will be equal to what? This is phi. Tan phi, you can write this quantity is VL minus VC, and this is VR, and I can write this is, you can write VL minus VC divided by VR. This is I XL minus I XC divided by I times R, and this implies your tan phi is coming out to be simply XL minus XC divided by R. Okay, so I got current, I got phase angle, I got impedance of the circuit. Now here first thing is, if you are asked to find the potential drop across any of these elements as function like okay, I got just the RMS value of the current. If V is the RMS value, if you are substituting here V naught, then it will be the peak value, and accordingly you need to calculate RMS value of the current. Okay, so this is all about up to here. Now I can calculate actually I, first function of time. So this is equal to I naught, and I naught will be equal to what? Let me write it here only. I naught will be V naught divided by Z. This is, you can write VRMS by, so RMS, then it will be IRMS, RMS, RMS. Okay, that's all. Alright, so we are up to here. Then what I can write for the complete circuit, you can see the I is what? It's lagging behind V by, if this condition is satisfied, by voltage. So I can write I is equal to I naught sine of omega t minus phi, or you can write it I is equal to V naught by Z under R square XL minus XC whole square times sine of omega t minus phi. This is the current in the circuit. Now for like I'm writing, in any case if you require anything about this circuit, and I think things are very simple, straightforward. You just need to approach properly. You need to proceed without doing calculation error, without missing something, is it? Then you will not have any problem. So if that is the current in the circuit, I will be the current, same current will be flowing in like a circuit. Then what I can write, we can calculate potential drop, the instantaneous potential drop. So VR is given by I into R, and that is equal to V naught R divided by, let me write it simply Z into sine of omega t minus phi, because you can understand potential drop across resistor will be in same phase as current. Clear? All right. Similarly, VXL or VL will be equal to what? So now here you must be remembering that VL will be leading the current by a phase angle of 90 degree. So here you can write it's V naught divided by Z multiplied by XL multiplied by sine of omega t minus phi plus pi by 2, because it's leading. And similarly we see, because here your voltage will be lagging the current by phase angle of 90 degree, so I can write this is V naught divided by Z multiplied by XC times sine of omega t minus 5 and minus phi by 2. So the phase angle between these two, you can see it's pi. So one is positive, then other will be negative exactly. So this is the basic things, simple things about the like straightforward things. Let me first calculate the power consumed in this circuit also. Then I will tell you something about this circuit. So I hope you are clear up to here with dealing with any quantity about this circuit. So power consumed in the circuit can be calculated. Power consumed in the circuit. So this P you can write V RMS I RMS multiplied by cos of phi. Clear? And this is average power, remember that. So VRMS is V naught, I'm writing it directly VRMS. IRMS you can write VRMS divided by Z, and Z is equal to under root Z is equal to under root R square plus XL minus XC whole square into cos phi. So what will be cos phi from here? Cos of phi, this is your Z, is equal to R divided by Z. Clear? So this you can write, this is equal to R divided by Z, and this I can write average power is equal to V RMS. I can write this is also quantity Z into Z, V RMS into Z into R. And this is what actually you can write average power is coming out to be I RMS square multiplied by R. So you can get it's effectively getting dissipated, getting used only across resistor. We calculated it for complete RLC circuit, but effectively it's coming out to be this, right? And here now, if I is maximum, definitely I can write my power will be maximum. So now the special thing about it, let's see some variations, then we will get some result. And that result you might be like already guessing, it's resonance in RLC circuit. So what it mean and how it happened, when it happened, let's talk about it. So this is up to here. Try to remember these relations. I'm now erasing it and I will be using them. Okay, so now let me tell you things in more detail to you. So let's talk about first is reactance of inductor. Reactance of inductor. So we know it's given by XL, and that is equal to omega times L, and this is equal to 2 pi F into L. Clear? And here you can see XL. XL varies directly proportional to omega or frequency. So if we look at its variation, then it will be straight line. This is XL versus omega or frequency. Clear? So here if we are changing the omega, if angular frequency is changed, frequency or angular frequency is changed, and if it is increasing, then XL will be increasing. So here for this circuit, if we are changing this source, is it volt frequency, things will change here, and that is how your XL will change. Clear? Similarly, I can see the variation of, so this is the variation of XL versus omega. Similarly, I can write reactance of circuit, or like I can say capacitor, just wait, reactance of capacitor. this is XC. So XC is equal to what? 1 by omega into C, or you can write 1 by 2 pi f into C. This implies XC is inversely proportional to frequency or omega. So if I plot this graph, XC versus omega or frequency, the graph looks like this. Clear? So here it's inversely proportional. So here, as your omega frequency increases, this XC, this I told you in terms of like all, when I talk about only capacitor circuit or reactive circuit, only inductive circuit, purely inductor, purely capacitor. So here in this situation, you can see when the frequency is high, its reactance means its opposition become low, means it easily allow them. So a capacitor is a high pass filter. And here you can see, if omega frequency is becoming high, its reactance, its opposition for that frequency will be very high, and it will try to block it completely. So in this case, it will allow more easily lower frequencies. So a purely inductor circuit is a low pass filter, right? Okay, we got this. Then I can write the reactance of this circuit. Is it? Reactance of RLC, series RLC circuit. So that will be equal to what? It's equal to X, T is equal to XL minus XC, or you can write XC minus XL also. Either way, depending on which one is greater. Now here I can see XT, reactance of the circuit, is omega L minus 1 by omega C. And if I plot its variation, then it will be what? Actually, like if I plot first both, this is XL and this will be XC, right? It's varying like this way, it's varying this. So now in this situation, you can see, if I cumulatively talking about it, this is the point where both, here you can write omega, is it? We call it actually omega resonance. I will define it later. Omega R. So at this point, you can write XL is equal to XC. Then at this point of frequency, your T, reactance of the circuit, will be what? Minimum. And before this, so I can write omega less than omega R, omega greater than omega R, effectively, because capacitive reactance low, inductive reactance high, so it will be like effectively like it will act like inductor circuit, and here it will be effectively a capacitor circuit. Clear? I can plot its net variation also. Remember these relations. So let me erase this part also. Now if I look at it, I draw it net Z versus omega, because we got Z is equal to what? Z is equal to under root R square plus XT square, and that you can write 1 this is also equal to under root R square plus omega L minus 1 by omega C whole square. So this graph actually almost looks like this. Whatever the omega, if it is like small omega, then also overall XT will be there, because in that case XC will be greater, dominating. If omega is high, then XL will be dominating, so still your XT will be something positive. So in both cases, you can see your Z will be what? Z will be higher, and at like exactly when this quantity is least, then Z will be simply equal to R, so Z will be your least. So if we plot the graph, then it looks like something this. This is your least value of Z, is it? And when omega is equal to, so at this point of time, this is again x L is equal to xc, and here your Z will be least and Z minimum is given by R. You can see it here, right? And if Z is minimum, I can write I will be maximum, V divided by R. Peak will be also maximum and RMS value. So I can, because I is inversely proportional to R, then I can plot its variation also. So it will be something like this. This is I max, I versus omega. So at this particular frequency omega R, this is omega R, we can say the current in the circuit is maximum, and current in the circuit is maximum, so power dissipation will be what? Maximum, because power is dissipating only across resistor, that is I square into R, so power dissipation will be what? Maximum, right? So I hope you are clear with this diagram. Let me erase that first. Okay, so similarly I can write the power, average power is equal to I square into R, RMS, and I variation I can see. So exactly in similar way your power will be also varying like this. This is your omega R, is it? So this is your P max, and P max is equal to what? P max is I RMS square into R, or you can write I max square multiplied by R. And what is I max? I max is equal to V RMS divided by R, not Z. Understanding? Because I max is equal to Z, but Z is equal to what? At maximum, it's equal to R. So means there exists one frequency, is it? There exists one frequency, is it? At which you can write xt equal to 0, z equal to, z is minimum, I is max, p is max, so on, and xt equal to 0. What is that frequency? Omega L minus 1 by omega c. Clear? And this implies omega is equal to 1 by equal to 0 under root LC. This is called resonance frequency. Frequency of series RLC circuit. So simple thing, this is your RS resonance frequency. At resonance frequency, Z is minimum, I is maximum, power dissipated in the circuit is maximum, and maximum power dissipated we got this one also, right? So this is, so if circuit is operated at this frequency, then in this circuit the power loss will be maximum, or power, you can say power consumed in the circuit will be maximum, current will be maximum, impedance of the circuit will be minimum. Now you try to imagine what is exactly happening at this moment of time or at this moment of frequency. What it mean actually, is it here xt is equal to 0? That means here we are getting what? xt equal to xl minus xc equal to 0, means xl is equal to xc, and I can write VL should be equal to VC because current is same, right? So in this at this moment of time, I am erasing this part now. At omega resonance frequency, is it? Here you can just try to imagine, normally this is the circuit and there is net potential drop across this. At resonance, you can write the circuit will be effectively this. Clear? And here it's plus minus VL, this is minus plus VC, and net potential V across this will be 0. So complete whatever the supply will be, V is equal to V naught sine of omega t in R. So complete supplied voltage will be actually applied across resistor. So at resonance, the whole applied voltage appear across resistor or resistance only. Net voltage across this will be 0. This is your resonance circuit. The next thing is why it is important. What is all about it? It's okay, there is resonance, there is something I will tell you, just wait. Okay, so first thing, I hope you are clear with the term. What is the meaning of resonance? What is exactly happening at resonance? How things potential drop and all those things, quantities are related. Calculating power, maximum power, normal way at resonance. I think you should be clear with calculating everything about series RLC circuit. Is it? So there is one more thing and few things more like that is called bandwidth. What is that? Let me tell you first. Okay, so RLC circuit and power we got, and here we define one is called half power frequencies. What is that? This is maximum power and that is omega r. So half power frequencies, the frequencies at which the power dissipated in the circuit is half of the maximum power is called or are called half power frequencies. Right, so let's calculate half power frequency. One more thing, this is like maximum power. I can write half power frequency will be here something, so definitely there will be two frequency actually, so that's why I will write R. Okay, so this is P max by 2. We got P max this. And what about here? One thing is here your impedance will not be simply R, it will be Z, is it? So at half power frequency, I can write Z will be my simply under root R square plus XL minus XC whole square. Right, and one more thing here we got at this exactly omega, my circuit is purely resistive, and here we have seen at high omega, high frequency, it is becoming inductive, XL greater than XC, XC greater than XL. So here it's inductive circuit, it's capacitive circuit. Right, that should be clear. All right, so in general term I can write both with this. Then at this point of time, what is I can write? P power is equal to average power is equal to what? You can write I RMS square multiplied by Z, is it? Or but I want this P should be half of P max, so that means half of P max is equal to I RMS square multiplied by right, I should be writing it okay, what will be my, this is VRMS into IRMS into cos of phi. I should write it better this. Is it clear? Normal power. And this can be written as actually, if I am writing in terms of cos phi, so it will be like VRMS I RMS into cos phi will be R divided by Z. That will be a, okay. So this I can write I RMS square into R divided by 2. This is P max into R to P max. This should be equal to V RMS I RMS divided by Z multiplied by R. I hope you are clear with this term. Next thing is I can write either VRMS in terms of IRMS and all that, or either I can simply, it's up to here. So this implies IRMS square into R divided by 2. This is equal to VRMS, and I can write it's IRMS. So this is V is equal to I. Just one second. Okay, so listen here. This is correct, but here your IRMS is not simple IRMS. It's basically maximum value, is it? So this can be written as actually I max square into R. This you can write V max also square divided by R. This you can write I max is I naught square into R, or this is V naught square by R, peak values, is it, in terms, and right, divided by 2 will be also there, by 2 because this is a R in terms of RMS value, maximum value. This in terms of peak value, it will be by 2, because this is equal to what, P max is equal to I like half of like it will be like half of I naught into V naught, or either we write it VRMS into RMS. So this is your maximum, but here half power, it's like normal RMS value and different. So here I can write it like it's simply I am writing it I, and this can be also written as I. This is I naught, that is maximum value, or V naught. So I naught, this is I square into R divided by Z. I can be writing it this way also, and one more, no, it's V into I into R divided by Z, and this can be written as, just let me erase it. Okay, so little bit confusion here, like let me clear it again. First thing is we got P max, that I can express I RMS, and this will be the maximum value also, and maximum value of RMS current is I naught, and multiplied by R you can write it V RMS square divided by R also, this I max square, and its RMS value. If I am writing it in terms of peak value, then it will be like I naught square divided by 2 into R divided by 2. Similarly, V naught square divided by 2. So here, if these are RMS and value of current and voltage at this omega, is it omega 1 and omega 2, then their peak value will be also there. So these are RMS value, then I can write it this way, and I can write it this way. So if I am writing it V peak multiplied by I peak into R, then it will be divided by 2Z, is it? And here peak value at this, either omega 1 or omega 2, this will be equal to what, I peak multiplied by Z, right? So this implies your P average power will be, I can write I peak square into R, Z will gets cancelled, divided by 2. Now the point is that this power at omega 1 and omega 2, is it? So this power P should be equal to half of P max. So let's get the peak value of the current at this power. That means it's like IP square into R divided by 2 is half of I naught square into R. So now if I simply like half of I naught, this gets cancelled, this implies I peak is coming out to be I naught by root 2. Clear? And we have already calculated here that I naught is equal to what? It's V naught divided by Z. V naught divided by R. But what will be I peak? I peak will be V naught divided by Z. Right? So now if I substitute things there, then this is I peak will be V naught divided by Z. Now I can substitute here V naught divided by Z is under root R square plus XL minus XC whole square. This is equal to V naught divided by root 2 into R. V naught gets cancelled and squaring on both sides, and I am writing it here. So this implies I am getting here 2R square is equal to R square plus XL minus XC whole square. Clear? Taking it this side, and XL is omega L minus 1 by omega C is equal to what? It's coming out to be R. Is it? Next I am taking its omega square into L minus omega C R minus 1 equal to 0, and solving this omega we are getting this is RC plus minus under root R square C square plus 4 this will be also C here LC divided by 2 LC. Clear? And here I will be getting 2 omega, so 1 omega 1 is getting RC plus RC minus under root R square C square plus 4 LC divided by 2 LC, and omega 2 is called RC plus under root R square C square plus 4 LC divided by 2 LC. So these are your omega 1 and omega 2. These are called half power frequencies. So we got actually half power frequencies, right? And then here, I hope you are clear with this term. So we got half power frequencies. So this omega 1 half power frequencies, omega 1 is equal to, I can write it by dividing, is it? It's R by 2L minus under root, this is R square C square plus 4 LC divided by 2 LC, and omega 2 is equal to R by 2L plus, and same thing, under root R square C square plus 4 LC divided by 2 LC. Clear? These are omega 1 and omega 2. What are these omega 1 and omega 2? Omega 1 and omega 2 are those frequencies at which the power in the circuit of power consumed is half of its maximum power. Is it? So here we define one bandwidth. Okay, now listen, let me tell you, so that will make sense to you. Actually, these circuits are used in our electronic instruments, telegraphy, and the radio you might have definitely seen before. Like earlier we used to have one rotor sort of thing. If you open it, inside there is one wire connecting with some coil, copper coil connected like this, and that when you are changing this channel on your radio, actually this changes, rotate. By this, actually in that circuit we are changing what? Frequency. Because RLC circuit is there, so there we are changing the frequency. And now there is one receiver which is receiving some signal from the radio stations or FM stations, and you might have seen they are set it from around 80 megahertz to some 100 and something or 80-90 megahertz to something like that. So now what happened actually, when there is some frequency or signal of some frequency from some particular channel, and the frequency that you are creating by rotating it matches exactly, at that time the circuit is in resonance. So circuit is in resonance at that time means the current of the power consumed is maximum, and then you will hear maximum power is there, then you will hear what? Clear voice, louder voice. Understanding? If it is not matching exactly, then it will not, frequency it's catching, but it's not amplifying that. Understanding? That frequency signal is not getting amplified. It will be amplified only when the current in the circuit, power in the circuit will be maximum. And that happens when there are only few frequency, and when you are, by rotating that, you are changing the frequency. So that is the application, that is the point. So half power frequencies means we calculate basically how effectively if the bandwidth of a circuit is very low, what that means it will catch things even better, the peak will be even better, understanding, it will not mix with something else. Now listen it, let's try to understand it. So if I'm having one circuit like this, where this is the maximum power and this is another like half power. Now if another signal, another channel comes here actually, then what will happen? It will, if this is the frequency, it will catch this one, it will catch this one also, then voice will not be clear. So if we are having a better like this circuit where the sharpness, we measure it sharp in terms of sharpness also. If sharpness of this circuit is low, I'm like basically I will write high, it's more steep, sharp, then it will more better selective. The selectivity of frequency of channel will be even higher. You can write the quality of the signal, the voice you will be getting even better. So that is the meaning actually here. So that's why we are calculating half power frequencies to have something idea about this circuit. I hope it makes sense to you everyone now. So now we got actually half power frequency, and bandwidth basically we define. So bandwidth is the difference in half power frequency is termed as bandwidth. The difference in half power frequency is called as bandwidth. Band, that channel, you might be band, change the band, change the channel, you might have heard that. So it's exactly that way actually. So bandwidth DTH of the RLC circuit. So what is the bandwidth? Here I can write bandwidth, this is omega 2 minus omega 1, and that comes out to be, if I'm simply this minus this term will be cancelled out, and R by 2L plus R by 2L. Right, just 1 second. I did some mistake. There is one more actually mistake, I missed something. So this is the relation we got, and here as I told, for omega less than this it will be capacitive circuit, so your XC will be actually effectively like leading, and for this XL will be higher. So I need to actually substitute things with this sign. So when I'm calculating this, it will be like for lower omega it will be higher, so I need to substitute. So if I'm using this XL minus XC, then this is the situation. So I will be getting like one higher XL minus XC I am using, so the higher one will be like omega 2, you are getting this way. Omega 2 we are getting RC, omega 2 we are getting RC plus under root R square C square 4LC divided by 2LC. This is okay, correct. Next situation, if we want to calculate actually omega lower, in that situation I should use this circuit for lower frequency, half power frequency. XC will be greater than XL, so I will be writing this 2R square equal to R square plus XC minus XL ka whole square. Now solving this, actually I will get, this is a same thing here, it is omega 1 upon omega C minus omega L equal to R, and from here actually you will get this is on that side omega square LC plus omega RC minus 1 equal to 0, and solving here we get actually omega 1 is equal to minus RC divided by 2LC plus under root R square C square 4LC divided by 2LC. Sorry for it, I did small mistake, I missed something. So this is omega 2 and this is omega 1. Now omega 2 minus omega 1, after solving this you will get this, then that is defined as bandwidth. So bandwidth omega 2 minus omega 1, you can see this minus this minus minus will plus, and this quantity will cancel, so this comes out to be R by L. So this is called your bandwidth, and we write it actually delta omega. So bandwidth of the circuit delta omega is given by R by L. So if you want to increase the bandwidth, you should have higher R. Want to decrease the bandwidth, better, like small bandwidth, L should be higher. So omega delta omega, you can write directly proportional to R, omega inversely proportional to R. Clear? So that is something special about it. And there is one more term, as I told, it's like steepness. We measure that in terms of like quality factor. So okay, the next term is quality factor. It is the characteristic of series RLC circuit resonance, or simply I can write RLC circuit. It actually about the sharpness of IV graph, and quality factor Q factor, it's defined as omega resonance divided by bandwidth. Omega resonance, we know actually it's equal to what? 1 by under root LC, and bandwidth we know we calculated R by L. So we are getting it actually 1 by R under root L by C. This is Q factor of a circuit. This is 1 by R under root L by C. Just remember these things. So this is all about your series RLC circuit. I hope there was just a little bit confusion about calculating half power frequency, but now you should not have any confusion. You just need to take care of the I maximum, or power maximum will be at I naught, means I naught is the peak value of the current, and that is maximum also. At half power, the maximum value of current will not be simply I naught, it will be something else, and that comes out to be I naught by root 2 we calculated. By using that, and another point you need to keep in mind is that here the system like XC will be higher than XL, so you need to write the impedance as under root Z square plus XC minus XL whole square. For this condition, it will be overall inductive circuit, so you should write it Z equal to under root R square plus XL minus XC. So just take care of that, otherwise you will also do mistake like me, so don't do that. And then I hope you also understood what is all about this circuit, where it is actually like working, and what the sharpness, what the bandwidth of this circuit is making like sense to you. So this is all about series RLC circuit. Let me solve some application, some problem based on it. Okay, see one problem based on series RLC circuit here. So a series resonance circuit consisting of 30 ohm resistor, 2 microfarad capacitor, and 20 millihenry inductor. So here we have LRC circuit which is connected to, and this is 9 volt is peak voltage, and here it's how much? R 30 ohm, 20 millihenry, 2 microfarad capacitor. All right, connected across series, okay, voltage and output this 9 volt. Resonance frequency, you are asked to calculate resonance frequency, current at resonance, voltage across inductor and capacitor at resonance, quality factor, and bandwidth. So straightforward things are there. We are supposed to calculate these things actually. Let's solve it. So now resonance frequency we know omega resonance is equal to what? 1 by under root LC. This is 1 by under root L, 20 minus 3 into 2 into 10 raised to power minus 6, 2 microfarad L into C. So this comes out to be how much? 1 by, this is power how much? 9. This then 8, 2, so it's 2 into 10 raised to power 4, right? And this is coming out to be omega R 5000 radian per second. Then you can write it 2 pi f resonance 5000, then F resonance is also coming out to 5000 divided by 2 into pi, and that will be 796 hertz. So it's like resonance frequency in hertz, resonance frequency in radian per second. So we got A. Next, current at resonance. So we know actually current at resonance is given by simply V divided by R only. So V is 9 divided by R is how much? 30. So 30, right, that's coming out to be 1 by like just 1 second, 0.3 ampere. This is the current. C part, it's saying right, voltage across inductor and capacitor at resonance. So voltage across inductor, so first we need XL and XC, we know both will be equal, and that is given by omega into L. Omega is how much? 5000 multiplied by L. L is how much? 20. 2 into minus 3. So minus 3 gone. So it's coming out to be 100 ohm. Then VL equal to VC. Phase will be like opposite, but magnitude will be same. This is given by I into XL, and this is I is 0.3 multiplied by XL is 100, that is 30 volt. Yes, it seems something different because we are applying only 9 volt and there it's appearing the peak voltage of 30 volt. That's possible in resonance. The voltage across inductor and capacitor may be greater than the peak voltage of the source. Alright, next it's a D, quality factor. So let me first calculate bandwidth. These are like bandwidth E. Bandwidth is given by delta W is equal to what? This is R by L. R is how much? 30 10 raised to power 30 divided by L is 20 into 10 raised to power minus 3, 20 millihenry. This comes out to be 1500 radian per second. We can calculate this is also equal to 2 pi f, or I will write 2 pi into delta f in terms of hertz. So dividing by this side 1500, this implies delta f is equal to 1500 divided by 2 pi, and this comes out to be 238 hertz. So this is your bandwidth, and let me calculate here quality factor D. So quality factor Q factor is equal to what? 1 by R under root L by C, right? And 1 by R 30 under root L 2 into 10 raised to power minus 6 divided by L to 20 into 10 raised to power minus 3 divided by 2 into 10 raised to power minus 6, and solving we get 100 by 30, that comes out with 3.33. So this is the quality factor. So this is all about series RLC circuit. Depending on whatever is given to you, I think you should be in position to answer, to calculate anything asked to you about the series RLC circuit. So ideally actually your topic, your concept finish here. And I can talk about parallel RLC circuit. That's not in syllabus, but sometime it may be used, so let me think about that. And this is all about AC. I hope you enjoyed it and solve more problems, practice more problems on it. It's a good topic, like questions are asked based on it. Okay, see you next class. Okay, next let's talk about parallel RLC circuit. It's actually not in syllabus, but I'm explaining it to you to, like, in case if it is required, not exactly in parallel RLC, maybe parallel RL, maybe parallel LC, something like that, then you should be in position to answer such type of things also. And it's like just simple straightforward method, nothing much complex here also. So let me just explain you, and before that I'm just defining two more things actually. One is called admittance. So what is admittance? It is denoted by letter Y. It is the reciprocal of impedance. So y is equal to 1 by z. Z you already know, it's 1 by r square plus xl minus xc whole square. So this is denoted by letter y. We call this admittance, and its unit, of course, it should be inverse of z, and that is equal to mho or ohm inverse, right? Another is susceptance. It is reciprocal of reactance, means x, and it's denoted by 2. So it's like a s letter. It is of 2 type, means susceptance for inductor and capacitor. So we call it inductive susceptance, that is Si or SL, that is 1 by XL, and it will be equal to what? 1 by 2 pi f into L. And another is capacitive susceptance, that is called SC, 1 by XC, that is 2 pi f into C. So here unit will be just inverse of XL, that is also same, MHO, Maho and ohm inverse. So these are just 2 terms. You will be like, if it is required, you must not be like getting confused and like you have not heard about it. Just few terms actually. Alright, so let's come back to here, parallel RLC circuit. So in this situation, we are applying this voltage across all 3 elements, and definitely because they are connected in parallel, so same potential drop will be there across each element. And to draw the phasor diagram here, we should draw the quantity on x-axis which is common, which is constant to all, and that is your voltage. So V here, the phasor diagram, let me first draw it. It will be V, right, voltage which is common to all. Now IR, that will be simply IR. What about current across inductor? Is it so? Instead of I1, I2, let me write IR, IL, IC. So what about IL? In case of inductor, your voltage lead, correct? So voltage lead means current lags, so that means your IL should be here. In case of capacitor, your current lead, voltage lag, so current should be leading, then it should be IC. Here also again, it may be possible IC is greater than IL, it will be effectively capacitive, and maybe condition IL is greater than IC, so inductive. All right. So in this situation, we got all these things. Voltage will be in same phase, but current will be like here, different way. So I can write for condition for this, so then it will be what? Like this is the phase phi, this is the voltage which is in same phase. Net current will be like depending on which is higher, either it is leading or lagging. If it is effectively capacitive circuit, it will be leading. If it is effectively inductive circuit, it will be lagging, right? So in this situation, I can write this is your net current I, right? And what I can write, I in this current in the circuit. So now again, remember here, now in this case, current we know, I told you already, it's a perfectly scalar quantity, but still we can't add these currents normal engines just simple scalar way, because there is phase difference. We will treat like vector and we will calculate net current like vector. So I in the circuit is given by under root IR square plus I L or IC minus IL whole square, is it? And what can be written as I is equal to, you can write V by Z, or I can write V 1 by Z is equal to what? Y. Similarly, IR is equal to what? V by R, or you can write V into G. G is called conductance. I can define one more thing here, that is, or you must be familiar with this term only. Conductance, it's reciprocal of resistance. So G 1 by R. Alright, so this and IC is equal to what? V divided by XC, that you can write V into SC. And similarly IL is equal to V divided by XL, that is equal to V into XL. Now I can substitute things here. Let me erase these terms. I hope you are familiar now with these terms. So you can write actually expressions in case of reactance and resistance and all those, and it's better sometime to write in terms of admittance and all that. So in this situation I can now substitute things here. So I is equal to V into Y, and that is equal to under root V into G whole square plus V into SC minus V into SL whole square. This implies your admittance is coming out to V getting cancelled, under root G square plus SC minus SL whole square. Clear? And this is the thing. So here you can see I will be also varying with like these things. I will be varying with, is it this quantity, because this can be like minimum and maximum. So here we write actually I minimum. For I minimum we can write what? IC should minus IL should be 0, then only your I will be minimum, and I minimum is equal to what? IR, and which is equal to what? V divided by R. Clear? And here this condition, this implies V by, or I can V into SC should be minus V into SL should be 0. This implies SC should be equal to SL, and this implies SC is what? 2 pi F into C minus, or I can write it omega into C minus 1 by omega into L equal to 0. So from here we are getting L. Omega is equal to 1 by under root LC. This is also called resonance frequency. Frequency of parallel RLC circuit. So here you can see the resonance frequency does not depend on resistance, and it's exactly same as it was in case of series RLC circuit. So we got this, we got impedance net circuit, impedance of the admittance of the circuit, like you can write in terms of impedance also, and voltage it's same across all. Current voltage we know already. Current you can write actually IR will be equal to what? IR is given by V by R. So you can get exactly this V naught sine omega t divided by R will be your IR. So here you can write IR is equal to V naught by R into sine of omega t. IC will be equal to V naught divided by X C into sine of omega t plus pi by 2, because here IC is leading the voltage by a phase angle of pi by 2. And similarly IL you can write V naught divided by XL into sine of omega t minus pi by 2. Clear? This is because we got it will be in same, and this current net you can write net current we will write only this way, magnitude, and the phase. So yes, if you are calculating these values, is it, if then you can write net current I will be equal to what? Something like I max sine of omega t plus phi, and I max you will calculate from here actually, I peak, is it, substituting these values. So this is about your parallel RLC circuit. I think you should be in position to even answer things related to this, whatever it's asked. potential drop, anything is like asked about to you. Power dissipated in each case, of course we know across L and C there is no power dissipation. Across R, then you can write actually it's V multiplied by IR, is it? So exactly that will be your power dissipated in RLC or parallel circuit. You can write here actually at resonance there is like these currents will be also here, it will be like current is one going positive, another will be negative. So actually if I talk about at resonance, then it will be one current going this way, another current will be going this way. So there will be current only on this, from this there will be effectively no current, only this will be the current. So at resonance I can write at resonance, what is the power factor? Power factor means cos phi will be equal to 1. So this is all about your parallel RLC circuit.